Welcome one and all. Today's topic is Intel 8086 microprocessor architecture. Myself Sridevi TR, Assistant Professor, Rajagiri School of Engineering and Technology. So microprocessor, by definition, it is a single integrated circuit or at most a few integrated circuit which incorporates the functions of a computer's central processing unit. That is a CPU integrated into a single IC or at most a few more ICs, that is called microprocessor. It's a multi-purpose clock-driven register-based digital integrated circuit which accepts binary data as input, processes it according to the instructions stored in its memory, and provides results as output. These are some of the features of 8086. It is a 16-bit microprocessor. So what do you mean by a 16-bit microprocessor? There are terms like 16-bit microprocessor, 32-bit microprocessor, 8-bit microprocessor. What do you mean by that? Actually, this bit, 16-bit microprocessor, if you say a particular microprocessor, say in this case 8086, if it is 16-bit, that means it is able to compute data which is of size 16-bit. In other words, all its internal registers, the data bus, etc., they are of size 16-bit. And you know that 6 registers are used to store the intermediate results of computation and to store the operands of a particular operations, etc. So in order to store that, you have a capacity of 16-bit registers. So the maximum data it can handle is of 16-bit. That's why it's called a 16-bit microprocessor. And it can support up to 64K I/O ports. So 64K I/O ports it can support, because again this port is of 16-bit. 2 raised to 16 is nothing but 64K. So 64K varieties of I/O ports. It provides 14 16-bit registers. It has got a collection of registers which can be used for general purpose as well as special purpose registers, and the total count of registers in 8086 is 14. And one of the most important feature of 8086 is it supports segmented memory scheme. What is its advantage? Using this segmented memory scheme, your 8086 is able to address 1 megabytes of physical memory. But you know that the computation capability of 8086 was only 16-bit. So with only 16-bit, you can have 2 raised to 16, that is 64K. But overcoming that limitation, 8086 can address up to 1 megabytes of memory. How 8086 is doing this, we'll be seeing in the later slides. So this is an architecture of Intel 8086. As you can see, there are two parts. First one, the top part is BIU, bus interface unit, and the bottom part is execution unit. We'll see this separately. And this BIU part, the top part, it handles all the transactions of data and addresses on the buses for EU. So we can say that this bus interface unit, it acts as an interface for your 8086 microprocessor to communicate to an outside world. Outside world means it can be a port, it can be a memory, etc. So what all is needed for execution unit, or what all is made as a computation done by EU, that will be moving in and out to the microprocessor through this BIU. So it will handle all the data and addresses on the buses for the execution unit. Like it will send addresses, It will fetch instructions from the memory. It will read data from the ports and memory, as well as writes data to ports and memory. Your BIU contains 4 components. You have a 6-byte instruction queue. You have some segment registers and one more register called instruction pointer, and then there is a special component called address summing block, which will do the memory segmentation for 8086. This is a bus interface unit. So this part, the 1, 2, 3, 4, 5, 6, it's written instruction stream byte queue. What is mean by this instruction byte queue is, BIU can take a buffer of instructions. It can take or it can prefetch 6 bytes of instructions in order to give it to the execution unit. Sometimes you might be giving an instruction to execution unit, and execution unit will be busy with executing that. It is not asking for BIU for any further addresses or any other data, but EIE execution unit is busy executing that set of instructions. Then BIU is free now. So at that time, BIU can prepare itself for the next request of EU. So once this current instruction is executed, execution unit will be asking BIU for the next instruction. So even before asking that, even before getting a demand from execution unit for the next instruction, BIU can prefetch that instruction from the memory and store it in this temporary space. So it can store up to a maximum of 6 bytes of instructions. If it is 1 byte instructions, it can prefetch 6 instructions in this queue. And there are a number of registers here, and as we discussed earlier, each register is of capacity 16-bit. The different registers here are data segment, stack segment, code segment, and extra segment, and along with the segment registers you have something called instruction pointer. So what is the use of this segment registers? In order to learn what is the meaning of or what is the application of segment registers, you need to address or you need to understand the memory segmentation of 8086. You can see here a memory interface. Through this interface, your BIU will be communicating to the memory. And we have also seen that the total memory which can be addressed by the BIU or 8086 as a whole is 1 megabyte of memory. So in order to address a 1 megabyte of memory, how many bits of address you need? It is 1 megabyte, that means it should be 2 raised to 20. 2 raised to 20 is nothing but 1 megabyte. So you need 20 bits to address 1 megabyte of memory. But what is the total capacity or maximum capacity of 8086? It can give only addresses of 16-bit or data of 16-bit, and its register capacity is only 16-bit. How you can transform this 16-bit address into 20-bit address? That will be done by this summation block. And each of the segment registers and your 1 megabyte of memory, that is divided into different logical segments. There are specific sections for data, code, etc. So here the BIU uses a mechanism known as the instruction stream queue, which we already discussed. It can see it as a pipeline architecture, and it can prefetch of up to 6 bytes of instruction code. And when BIU is busy executing, BIU is free to look ahead in the program by prefetching the next sequential instruction. Then the segmented memory. It supports segmented memory scheme which can access to 1 megabytes. All these things we discussed. So here there are different segment registers in BIU. And I told you your 1 megabyte of memory is divided into different segments. You have a data segment in which you will be storing all the data required for your program. And you have the code segment register where the executable program is stored. Then extra segment where another data segment in the memory, when it's mostly for string applications, etc. Then you have the stack segment register, which is used for addressing stack segment of the memory, which usually to store the stack data. So if you take a application program, let's say int a equal to 10, and then you're doing some operations on that int a, and you're trying to do int a equal to 10, int b equal to 5, and then you're trying to get the sum of this a and b into a variable called sum. So in this case, if you will be converting this application program into an assembly level programming, which you already know, in order to and finally into machine code instructions for the computer to understand it and execute it. So if you take the simple application program, what are the code segment part and what are the data segment part? If you give int a equal to 10, int b equal to 5, all these variables which is defined by the names a and b, that has to load into that part of the memory which is intended for data, and that part is called the data segment. So your data segment will have separate locations which is allocated for this variable a, variable b, which is holding the value assigned by you in your program. So there is a memory space for a which is having the value 10, then b with having the value of 5, and after the execution of the instructions or the program, you will have a sum variable location with the value 10 plus 5, 15. So all these will be having your data segment part, and all these instructions, application level programs, that will be converted to different assembly level programs like load a with the value 10, all that things. So all that instructions, executable program, that will be getting stored in code segments. And sometimes you need extra data segments, mainly for string applications, and also that data will get saved in extra segment part. Then similarly you have stack, where stack will come into picture for programming. You suppose you invoke a subroutine call, so that when you invoke that subroutine call, you need to come back to the previous location from where you call that subroutine, right? It is like you have to store that address or store that instruction. What is the address of the next instruction you are supposed to execute once you come back from the subroutine, once you come back from the execution of that subroutine? So that part will be saved in the stack. So once you so that address of the next instruction after the call, for example, say call add numbers. Add numbers is the subroutine. So that part, when a call instruction is encountered, the 8086 will move to the address of subroutine instruction. Subroutine, that set of instruction which constitute that add numbers subroutine, and it will be executing that. After that, suppose you have another one like move a comma 10, something like that. You are moving the value 10 to a register called AX. So here, once you finish execution of that subroutine, you need to come back to the next instruction after the call, that is move a comma AX, move AX comma 10. So that address of move instruction should be stored somewhere, so that you are actually pushing to a stack, and once that subroutine is executed, you will pop the data from the stack, and that address will give you where is your next instruction after the subroutine call. And so your entire physical memory, which is of size 1 megabyte, there are two types of memory segments, like how you can divide your 1 megabyte of memory into different segments, like data, code segments, etc. So here, sometimes your segments can be overlapped, and some other times it should not be overlapped. Then it's, as the name suggests, non-overlapping segments. There should not be any overlapping. That is, suppose there are two chord segments in your entire memory, and so this chord segment is defined by CS1 and offset IP1. we'll discuss what is offset and all. So here CS1, that will give you the beginning part or the beginning of that particular segment. So usually segment registers holds the beginning address of a particular segment. So data segment register will hold the beginning address of data segment. Code segment register will hold the beginning address of code segment, like that. So it's so possible that from different like processors or different users or whatever it is, your memory can be shared, and different code segment registers can hold the starting address for different code segments. See, you have to understand one thing. All these segments, data segment, code segment, etc., they are not physical classifications. They are just logical classifications. It is like suppose you have a big housing colony, and you need to go to a particular house called 79. So if there is no segmentation, or if there is no division like cross number 1, cross number 2, cross number 3, like that, it is, you have to start from the house number 0, and then you need to search for this particular house number called 79. But suppose there is a segments, or in other words, in terms of housing colony, suppose there are different crossroads. In order to go to 79, you can first reach the crossroad 7. So from there it's so easy to go to 79. So it is actually a logical classification of your entire memory, like CS1. And then, so you'll be reaching the beginning of that particular segment by using your code segment register value, and from there you have to go to some more time. Like for example, suppose your code segment register was that street number 7, and then from that beginning of that street number you need to go further to 79. So how far you need to move, that will be given by the offset register. And corresponding to each segments, like for data segment you have another offset register. For data segment and code segment, you have got different offset registers. For stack segment you have a offset register, etc., etc. So like that you will be calculating the effective address, so how far you have to move. So this is the effective address calculation, which will be done by that summation block you have seen in the BIU part. So here the segment register, which is of size 16-bit, which indicates the starting address of a particular segment, you will take that value, you will left shift it by 4 bits. If you left shift it by 4 bits, what is the resultant capacity? It is 16 plus 4, that is 20 bits. What's our ultimate aim? You need to convert your offset address into a 20-bit address. With this 20-bit address, you will be able to address 1 megabyte of memory, because 2 raised to 20 is 1 megabyte. So just left shift it by 4 bits. So you know that your LSB, 4 bits from the LSB side will be becoming the 0 bits. Okay, the 0 MSB bit, sorry for that, MSB bit will become 4 zeros. And after this, the offset address, for corresponding to each segment register, you have an offset register. That value will be taken and that will be added. So when you add a 20 bits plus 16 bits, you will be getting a 20-bit effective physical address. This is an example. Suppose you had your CS register filled with 34BA. That was the code segment register value. And you need to move to a particular instruction which is defined by an offset address of 8AB4. So in order to move to that exact location of that particular instruction, first you need to left shift your code segment register value by 4 bits to the left. So here you have left shifted it by 4 bits. So it is actually a hexadecimal notation. Please note that this is hexadecimal notation. So 4 zeros are defined by only a single 0 here. Okay. So while adding, this is what you get, and this is the exact physical address which can be which is understandable by the memory segment like 3D654. The memory segment will directly go to this location and will pick up the data which will be of an instruction type, and that can be fetched. So these are the segment and offset address register combinations. For CS, you will have the offset address stored in IP. For stack segment, you have it in the stack pointer and base pointer. For data segment, you have BX, SI, and DI, and for extra segment, you have DI. So these are the different combinations. And then you have seen you have the execution unit, which will decode the instructions fetched by the BIU. Very simple, like all the address summation block has calculated the effective address, and so the execution unit will be giving only the offset address of either the instruction or the data, whatever it requires. It only handles offset addresses because that's all it can do with its 16-bit capacity registers or data bus. So it will be giving the offset address, and it is a BIU which converts that um, offset address into a physical effective address. So here the execution unit, it gives different parts, like you have a control unit which will decode the instruction, and depending on the decoded instructions given by the BIU, it will generate different control signals like read, write, etc., and it will given to the arithmetic logic unit. And you have the instruction decoder, as I just explained, and you have an arithmetic logic unit which will do all these arithmetic and logic calculations with the help of some of the registers here. You can see AH, AL, BH, BL, etc. They are all general purpose registers, and you have stack pointer, base pointer, etc., which were the offset registers for different segments which we have seen in the last slide. So these are the different registers of 8086. It's classified like general registers, index registers, segment registers, pointer registers, flag registers, etc. And you can see here your AX register, it is of size 16-bit. But for our ease of calculations and computations, you can even divide that 16-bit register into two parts, AH and AL. The lower part of 16-bit, which will give defined by the name AL, and the higher part of AX is AH. Why do you want to divide it? Because sometimes you don't need a 16-bit computation, you are happy with an 8-bit computation. You want to add to 8-bit data. Do you need to use that entire memory capacity of that register? No. That can be the other 8-bit part can be used for some other operations. So that is that AL and AH. Similarly for BX, CX, DX, etc. So these are the various general purpose registers and their applications. AX, it's a 16-bit register, so it is required for word multiplication, word division, and word IO, etc. So if you have to read a word from any input device, you need to store that data into an AX register. Similarly, if you have to read a byte data, a byte division, or any byte manipulations, you can go for only half of either the low part or the high part of AX. Since 8086 gives you a provision for dividing the 16-bit register into two halves, the lower half and the upper half. So you don't have to waste the space of register if it is a byte based computations. Similarly, BX, it is for storing the address informations. It can store the logical address or the offset address into BX register, which can be taken over by the BIU, and effective address can be calculated. And since you for the program, sometimes there will be loops, like the same set of instruction has to be repeated a number of times, so that how many times it should execute, that should be a loop count. So that loop count can be stored into a register called CX. And sometimes you need to shift or rotate the variable, like if you have to for doing some multiples of 2 and all, it you know, there's a left shift and right shift which gives you multiples of 2 and divided by the different 2's. So all that things comes in the count registers, variable shift and rotate. And then there is DX registers, that's for word multiplication. Wait. So this is the different address general purpose registers and their applications. You all know that the registers of 8086 is 16-bit registers. But if it is a byte-based data, you don't have to utilize that entire 16-bit. So 8086 gives you a provision for make the entire 16-bit into two halves. The lower half for an AX register, it's termed as AL, and the higher part is termed as AH. So all the byte multiplication, byte division, etc., you can utilize these 8-bit registers, half registers you can call. So this if it is word multiplication, if you have to read a word from an input device, or you need to write a word data into an output device, you can go for the AX registers. And BX register, that is mainly used to store the offset address information. So the BIU will take up this offset address, and it will do the address summation block, and it will calculate the physical effective address to take or write something into the memory. Then sometimes for your program you need to execute, or you need to repeat a set of instructions multiple times, or you need to do a loop. So that loop count and all can be stored into a register called count register, which is given as CX. And sometimes you need to do the shifting of the bits and or rotation of the bits, etc., for various purposes. So then we can go for the CL register. And so DX register, it's to hold the IO address during the IO instructions. So if it is the result is more than 16 bits, the lower order 16 bits are stored in the accumulator, and the higher order 16-bit registers will be stored in the DX register. We have also pointer and index registers, which is used to mainly to keep the offset addresses. And so this index registers SI and DI and BX, so generally default to the data segment register. So if they have an offset address, in order to get the effective address calculation, that will be added to the 4-bit left shifted data segment register value. So it is pointing to actually things stored inside the data segment register. That offset will be given either in SI, DI, or BX register. And similarly, for the stack segment registers, you have two pointer registers: stack pointer register and base pointer register. So stack pointer register, it's used with the stack segment address, and it is used to access that stack segment. It will reach to that particular location of the, it will take you to that stack segment where it is saved in that entire the stack segment address. And base pointer register, or termed as BP, it is pointing to the data in the data segment. So unlike stack pointer, we can use the base pointer to access data in other segments as well. So that's one of the difference between stack point register and base pointer register. This SI and DI, we already discussed their index registers, and basically they are used when string operations are involved. So this SI will register will point to the memory locations in the data segment, and which is addressed by the ES register. So I told already we have discussed that this extra segment register, they are also used to carry or to load the data. And this so this SI will be pointing to the memory location in the data segment which is addressed by the ES register. And this DI associated with the DI or destination index register, that's also required for some string operations. So this when string operations are performed, this DI register points to the memory location again which is addressed by the ES register. And so both SI and DI, they are associated with extra segment in the string operations. And both of these index registers may also be used to access the data stored in the arrays. We have the execution unit. One important component is flag register. A flag is you can consider it as like a flip-flop which indicates some conditions produced by the execution of an instruction or controls certain operation of the execution unit. So you can treat a flag register as again another 16-bit registers, and each bit of these 16 bits, it carries some meaning. There could be status bits or there could be control bits. In 8086, 9 out of the 16 are active flags and remaining 7 are undefined. They're unused. They are reserved for future uses. And out of this 9, 6 flags indicate some conditions like whether the previous instruction has resulted in a value of 0 or whether the previous instruction execution has resulted in a carry generated, etc. All these things after the performance of the execution unit in the previous instruction, that will be updated in these flag bits. So seeing the flag bit, we will understand what was the outcome of the previous instructions. So that accordingly you can go for the next step. And so there are 3 control flags also, like trap flag, overflow flag, direction flag, etc. So here out of this there are like a carry flag, all these things we already seen. This carry flag, it holds a carry after the addition or borrow after the subtraction. And a parity flag means it counts the number of ones in your result, and if this it's even number of ones, you have got a parity flag as 1, otherwise 0. And carry flag is set when you have a carry after your 7-bit, whereas auxiliary flag, it's set to 1 when you got a carry between the bit positions 3 and 4 of the result. It's useful in BCD addition or subtraction. Then 0 flag, it's a result of arithmetic or logic operation. If it resulted in 0, your 0 flag will be set to 1. And sign flag, it's a sign of the result after the arithmetic and logic instructions. So if it's negative, it is equal to 0, and otherwise 1. Then the control flags, trap, interrupt, direction, overflow, etc. So trap, if you have to debug, implement the debug on chip debugging feature, it can be enabled. The trapping can be enabled by setting this flag to 1. And if you have to interrupt the 8086 processor while running for a more priority work, then you have to set the interrupt enabled flag as 1. And direction is either we have to, in the memory, if you have to proceed in the forward direction or the backward direction, that can be set by this direction flag. And overflow occurs when you have sign numbers are added or subtracted. So in this trap flag, interrupt flag, and direction flag, they are the 3 control flags. Rest and all are the status flag, and the rest are unused and reserved for future purpose. Just an example here. 6 of the flags are status indicators. So here you have register AL carry a value 7FH It's hexadecimal notation. So 7F means 7 will take 4 bits and F will again take 4 bits. So altogether it takes 8 bits. So it's well and fine with an 8-bit register of AL. And then you have an instruction add AL comma 1. So what does that instruction means? You have some contents in AL. That content will be taken up. That will be incremented by a value of 1, and where the results go, that results will get saved in AL back. So what happened to the previous value of AL, that was 7FH, that will be overridden by the new sum. So your new AL value will now become 80H. 7F plus 1, that is 80H. Has it created any carry? No, it's perfectly well inside the AL. So you have carry flag equal to 0. Just count the number of ones here. It is only 1. For 8 it is 1000. There is only 1 there, and then again 000, no ones. So altogether you have only 1. So it is it's odd number of ones. So your parity flag will be 0. And there was a carry generated out of the bit 3 into bit 4. So your auxiliary flag also will be set to 1, and the result is not 0 here, it is 80H. So your 0 flag will remain 0. Sign bit 7 is 1, and sign bit has changed, so your overflow flag will be also set to 1. So that's all for the architecture of 8086. Thank you for listening.